chemical kinetics. Oops. What we're basically talking about with chemical kinetics is how fast does a reaction occur? How fast does it get from one place to the other? We know up to this point, we know what our reactants are and what our products are, but we don't know how fast they get there. Like, for instance, diamond is an unstable form of carbon, and it should decompose in an oxygen atmosphere, but it will take a million years to get there, right? So the reaction rate has a bearing on well, let me put it another way. Reaction rates is a piece of the puzzle. We know where we're headed, we just don't know how fast we're going to get there. So study of reaction rates, chemical kinetics, is how we address that question. Okay, so we need a way to express that rate. One way is to say, how fast does a product appear from a reaction? Put two reactants together, then initially you have no product, right? So how fast does the product appear? The other way is to say, well, how fast does the reactant disappear? And it just depends on how you express it. If we say, let's see, this doesn't make a distinction. It just says concentration of some component minus at the final time minus concentration at the beginning time. This is probably disappearance of A. That's what I think, that's what's happening. So if A goes to products, and then we say, all right, what's the concentration of A at time? And we use square brackets to mean concentration. So the concentration of A at time 0 would be a certain amount, right? X 0. And then later on, we measure the concentration of A at whatever the time 1 is. Let's just say minutes. Okay, after a minute, you got this much. Well, the final minus the initial would be an expression of the change of concentration. Or we should say the change of A. Change of A is equal to the final minus the initial over how long did it take, change in time. In this case, it'd be 1. Now, if we're expressing this in terms of disappearance of A, then 1 would be smaller than this one. So there'd be a negative value, and a negative rate would be the disappearance of A.
I leave you with the answer.
I'm sorry?
I leave you with the answer.
The rate.
Yeah, because it was very.
Yeah, that's the rate. And that's the rate over that period of time. The thing about reactions is that the rate of the reaction is not linear usually. In other words, in the beginning, it might be really fast disappearance. And then later, it might be a slower disappearance, slower and slower. So it's not a linear function, usually. And we're going to talk about those variations in a minute. But just as a basic expression of reaction rate is the change of concentration of A over a certain period of time. And very often we use molarity, moles per liter, as our constant, even for gases. Although sometimes it's more convenient to express the concentration of gas in partial pressure. Okay, So here's an example, the nitrogen dioxide. Okay. Try another one. I don't want that color. Black, black. Nitrogen dioxide. So what's the reaction? Well, nitrogen dioxide is decomposing, right? So it's just a single reactant, and it's changing to nitrogen monoxide plus oxygen. Okay, so that's the reaction. The overall reaction expression is here. And if we start our timer here at 0 and measure it every 50 seconds, then we get, if we start off with a concentration of nitrogen dioxide here, it's decreasing gradually that way, which means we start off with 0 products and then we're gradually creating some over here. What you'll notice is, what's the difference between 0.01 and 0.0079? Right? It's 0.0021, isn't it? So notice that the ratio here is 2 of these and 2 of these. That means if this difference is 0.0021, that means this concentration will be 0.0021, and this one will be half of that, 0.0011. So it's got to show up somewhere. And you can make those comparisons all the way down. What's the difference between each one? It shows up over here and you add it up. So this would be a data set for reaction rate. What you'll also notice is that if this is the reactant and these are the 2 products, notice when you start off here, you've got all of this and none of that. And then gradually you start adding in, you start building up product as the reactant disappears. So what's the rate? Well, like I said before, this is not a linear rate. Right? The rate of change, if this is time and this is concentration, then the rate of change is the slope of the line. But it's the slope of the line at that point, or the tangent to that line. So it's really high up here, but as you get less and less, the slope shallows out. And the slope is less and less and less. Here it's very steep too, and then it decreases. So you probably understand the concept of tangent to a line.
I understand what tangent is.
Yeah, okay. So the rate of change at this particular point is the slope of that straight line tangent to that point. Okay. What we call instantaneous rate. That seems like a misnomer, right? How can you have an instantaneous rate if you don't have a change from here to here, right? At that instant, you're just at a point. So if you stop to think about it, it'll mess with your head. But what we're actually saying is the slope of the line at that point. That's an instantaneous rate. Okay, so with every reaction, as written here, there is a rate law associated with it. And the rate law is written as just the rate equals something. And the rate is equal to some rate constant, characteristic of this reaction, times the concentration of whatever you're measuring. In this case, we measured the disappearance of this, and then to a power. That's called the order of the reaction. We try to look at orders as whole numbers, but they don't have to be whole numbers. When we're talking about them in the subsequent slides, we're going to try to stay within whole numbers. But what we'll find out is when we do this experiment, this rate experiment, when you calculate the order for one of the components, it probably won't come out a whole number. One of them will, because there are 2 components. You got the color and the bleach. So their concentrations matter. One of them will figure as a whole number and the other one will be some fraction. Okay, so when you're asked to write a rate law, that's what they mean. Right? You got a rate constant, and you have a concentration of the reactant, and there could be more than one reactant out here, depending on the equation. And each one of these terms will have an order associated with it. Okay, so for this very simple case, that's the rate law. And then what we need to do to fully describe the rate of that reaction is find out what this value is and what that value is. Now, as a practical matter, and to make sure that the mathematics don't become too complex, we study what we call initial rates, which means we study what's the rate of the reaction at the very beginning. And we do that because if we look at this reaction, we know that once you start building up products, you can get a reverse reaction. They can start going back to the original. Now, the significance of that reverse reaction depends on the reaction itself, so it's very specific. But in order to study the rate here, we look at the initial rate, where there's none of this and there's that, or there's just very little of this at the very beginning of the reaction. And that makes it more manageable. Another important factor is that this order cannot be determined from the balanced equation. It's completely independent. This has to be empirically determined. You got to run the experiment. You may have to run it several times at different concentrations and then figure out what that n is. You cannot write it from the balanced equation. Okay. So when we write this rate law, as written now, this is called the differential rate law, the way it was written with the K concentration to the power of n. And this is true, but as it's written, it shows that it's dependent upon the concentrations of reactants. Right? Sometimes it's more informative to have a time term in there. Right? And then what we do is we take the differential rate law and we integrate it. So these are calculus terms. So if you never had calculus, it may not mean much to you. You had pre, okay. So you sort of had to dip your toes in the water.
I had calculus in high school, so I assumed it's pre calc.
Oh, okay, okay. So you've heard these terms before, differential versus integrated. Okay. So we can express this differential rate law in an integrated form, and sometimes that's much more useful. Oh, well, here's a summary. This is initial rates, right? That's what that expression is. And then this is differential and integrated. They're like flip sides of the same coin. And it depends on whether you want to get at concentration only or you want to get at a time value, where the integrated rate law will be more useful. We haven't got to it yet, but most reactions do not occur in a single step. In other words, when we look at this equation, there's a whole lot going on right in there. Right? This may go somewhere and then somewhere else and then somewhere else and eventually end up here. We call that mechanism. So those steps to the mechanism.
Like that one lab we did whenever we put that one liquid intervened.
It was an acid-base indicator.
I think so. I don't remember what it was called. I just remember that we put one liquid into the other liquid. turned pink. And we kept turning on and off until eventually the whole thing just one drop turned the whole thing pink.
Oh, no, that's titration.
Yeah, but that's like, sort of like that, because it's like,
Mm.
it's a reaction.
It's a reaction, yeah. But what I'm talking
So
about
now
is,
you're talking about product.
what I'm talking about is steps. Like this might go to some product up here, and then that goes to another product, and then that goes to this one.
Whenever you said mechanism, I thought you were talking about like how we had to keep.
No, mechanism,
Turn it from product to product, to what you eventually want, I understand that.
yeah, from reactant to product, and it goes through several steps, maybe only 2 steps, but sometimes 3 and 4 steps. When you do that, let's see. Oops, wrong way. Here we go. If you know what the mechanisms are, those steps, then you can correlate the balanced mechanism steps to the reaction, the rate law for that individual step. But the overall has to be empirically determined. But the individual mechanisms can be inferred from the balanced mechanisms equation. Okay, we'll get to that in a few minutes. Okay. So when I talked about initial rates, in other words, we start off with only reactants and no products, and we measure the initial rate at the beginning. There's a method associated with that, obviously called method of initial rates, but it's more than that. We start at time 0, but we vary the concentration of the reactants, holding this one constant and let this one vary from here to here. And then we hold this one constant and vary this one from here to here. And that way we can correlate what's actually going on. Because if this one is constant and you're changing these two, then you don't have to worry about what's happening to this one. But if you hold this one constant, then you can say this one changes from here to here. And you can use that information to figure out what the order is for each of the reactants. It'll make more sense when I show you an example. Okay. So, like I mentioned before, you can have more than one reactant in your rate law. This one has 2 reactants, and each one has its own individual order. So the order with respect to A is N, and the order with respect to B is M. The overall order is just N plus M. Yeah. So if this order was to the power of 1 and this one was 2, then the overall would be 3. Just a refresher. For the overall reaction, how do the exponents in the rate law compare to the coefficients in the balanced equation? They don't. For the overall reaction, they're unrelated. And the reason is that in the balanced chemical equation, those coefficients are an expression of stoichiometry. They're here we are, now here we are. Doesn't say anything about what happens in between.
Talk about stoichiometry a lot last semester.
Yeah, we did. We need to know something about the mechanism before we can relate any of the balanced mechanism equations to the rate laws. And we will do that. Okay. So we're going to look at 3 different characteristic orders. One is called 0 order. That's where the power of the concentration is 0, which means what?
Just be 0.
It means, yeah, it means that's 1. Anything to a 0 power is 1. So that's why it's just K. So the rate is K. Now this one is a linear expression. Yeah, I mean, it's the rate varies with the independent of what the initial concentration is. It's always the same rate no matter what you start with. And if we take this one and we draw let's see, concentration of A with time.
If you can out from the top because it's negative.
Yeah, it should be like this. If we integrate that, we get negative K is the slope of that line.
That's like a little bit.
This is more like statistics.
Yeah, that's what I was meaning.
This is-
I'll talk triangle, so maybe
This is a regression analysis. If you have, I don't know if you've gotten to that yet.
I don't either. I did the test last night and I can't really think about it.
Okay. So the integrated version of that law is this, where you have y equals mx plus b. So it's going to intersect the y-axis at a 0 and the negative slope. Okay. So if we know the slope of that line, we can figure out k, and k goes in here. What we have to say is, determine is it a 0 order? And the way you do that is you just, you get your list of numbers, your data, concentration versus time, and plot them. Right? Concentration versus time should be a straight line. If it is, you know you have a 0 order. Like that. Oh, yeah. One other thing that you can tell from this information is the half-life. Now, I don't have time to go into the derivation, but the half-life of a reaction, you know, is
This is what I studied last night.
how long? Yeah.
Yeah, I remember, because I remember being a half-life in a question. I was like, yeah. Because
How-
I remember going over that last night, but I just didn't think anything of it. I was trying to hurry up and study for the test.
So half-life is defined as how long does it take half of the initial reactant to disappear. That's the half-life. Like half-life in radioactivity. How long does it take for that isotope to decrease its radioactive output to 1/2 its original? So this is chemical half-life versus nuclear half-life.
What nuclear really longer?
Do what?
One of the nuclear half-life like bigger, like longer.
No, it varies all over the place. Some nuclear half-lives are milliseconds,
Really?
and some are days, some are years, some are thousands of years, some are millions of years.
I expect them to be like really big because like nuclear energy is like,
It depends on the isotope.
but I'm sure they all give off a good amount of energy.
Well, it depends. Depends on what it is. Yeah. Okay, so the expression of half-life for 0 order is the initial concentration divided by 2 times K. So the half, so the half-life,
Really low answer.
the half-life does depend upon the initial concentration. And then you need to know the K value.
But it's gonna just be 1 divided by whatever 2 times the K value is.
Well, no, you need an actual value to find the half-life.
Also, that's not even to 0 power anyways, so I thought that
No,
was-
this is initial.
Yeah.
Yeah, at time 0. So the initial concentration divided by 2 times K will give you that. So the nice thing about this reaction, this equation is, if you know the half-life and you know the initial concentration, you can calculate the K.
Oh, yeah.
Or if you know any 2 of them, you can find the third one.
Just have to know how like remodel it.
Right. You have to know, is it a 0 order? Right? Or is it, we're going to look at first order and second order in a minute. Or is it first or is it second? They have different half-life equations.
How do you know which one is?
I'm going to show you.
Okay.
It's coming. Okay, Now for a first order reaction, the rate law has the first order power of A times K. And for these zero first and second order equations, we're talking about the reaction rate reference to only one reactant. So if there are two reactants, then I have to explain how to tease that information out, because you're going to need to know that, because next week that reaction does have two reactants. It's got the color, it's got the bleach. So I have to show you how that works.
I said it's gonna be a sticky lab.
It could, yeah. You don't want to get it on your fingers or they'll stink forever.
Won't bother me too much. I hope anyways. I have like this hand soap at the house. It smells really good. So I'm just hoping the tires bleach when that happens.
Let's see, this is, let's see. This is zero order. First order, if you plot A against T in a first order reaction, it's going to be a curve like that.
Last night, whenever I was studying for what I thought was gonna be this test, and I was
Okay.
studying for that one. I was like looking at the answers and I was like, what does it mean? Zero first and second, where's the third? And stuff like that. But
They exist. It's just, it's too big a field for us to cover the
I
whole
didn't even
thing.
know I was studying this stuff either though. I don't know. Like I said, I was out of it last night too,
So
because it was late.
when we integrate this rate law, we get a linear equation if we transform the A into natural log of A. Okay. That's not the common log, L of G. This is Ln with the base is E. Okay. So if we plot the natural log,
That's not calculus too.
yeah, if you plot the natural log of A, you get a straight line with a slope of negative K. Okay. Right, so if you plot your data, the raw data, and you get a curve, you know it's not zero order. If you transform the A into a natural log of A and plot that against T, and you get a straight line, you know it's first order.
So if you plot the first order against the second order, it's this straight line, it's the first order.
Yeah, you get this straight line with a natural log. Then well, that's what it would look like.
But if it's a curve, if the natural log plotted against the zero log is gonna be a curve, it's the zero.
If it's curve with the raw data,
Yeah.
then it's not a zero. If you transform it into a natural log and you get a straight line,
It is a.
it's the first order.
Okay. I thought you were saying that if it's a curve, whenever you plot it against the raw data, it's a zero, but I got it wrong.
The other way around. What was that all about? I bet it was an email. No? There's nobody there. Okay. I don't know what it was. Okay, so the half-life is an expression like this. The half-life of a first order does not depend upon the initial concentration. It's nowhere in the formula. It just depends on K, the inverse of K. You divide that into 0.693 and you got the half-life for a first order.
That one's gonna be a lot easier to figure out.
Yeah, yeah. Now, how about, oh, I see, we're gonna do an example for a first order reaction. A first order reaction is 35% complete at the end of 55 minutes. What's the value of K? Okay, we're told it's first order, so we don't have to plot it. We know it's first order. So that means we've got the rate equals K times A to the first order. Or we've got the natural log of A equals negative K T plus natural log of the initial there. Or we've got a half-life equals 0.693 divided by K. We got all those at our disposal. What we need to do is say, all right, what is this telling us? If the first order reaction is 35% complete at the end of 55 minutes,
You have to use the safety rules.
we can set it up like this as the concentration of A versus time. At 0 time, what do we have? Well, we have some value, right? We have initial value. And then after 55 minutes, right? What do we have down here? Well, if it's 35% complete, how much do we have left? 65%, or 0.65 times the initial is what we have left. Then what we can do is say, all right, can we use the value? We were looking for K. So which one of these can we use? This one has time in it. This one has time if it's a half-life, but it's not a half-life. It's 0.65. So maybe we could use this one. Right? The initial is this, and this. So if we put this on that side, it would be this one minus that one. Right? It would be natural log.
Well, we just added each side anyways. So we have to find the K. I was thinking wrong.
Well, if we did this one like that, and then we said this one is negative on this side, then that would be minus KT, right? But when you subtract the log from log of one from log of other, it also means log of A divided by log of A0, or log of A divided by A0. Huh?
So we subtract the logs, you divide them?
Yes.
Huh.
If you combine them, that's a log rule. Minus KT. But we know the ratio of A to A0 after 55 minutes is 0.65. So this is log of 0.65, right?
Equals negative K, right?
Negative K after 55 minutes.
Okay, I was curious if that, please.
Yeah. So now if we take the natural log of 0.65, I hope I'm doing this right.
Well, we have to divide that by 55 then? Or subtract
After we
5?
take the log of it.
Oh, yeah, after we do that.
Yeah. 0.65 and then
Will we
natural
divide
log.
the 55 or subtract the 55? Oh, yeah, we divide it because it's trying to multiply by K.
Right. 55 divide. Okay, so that's minus 7.83 times 10 to the minus 3.
Be positive, because
Minus
divide by negative K anyways.
Oh, if we took this negative over there and left the K alone, yeah. Yeah, that's all right. The negative 55 divided into that would give us 3 times 10 to the minus 3 equals K. Now let's see if I did it right. Okay, I went a little overboard. The ratio here, there's the ratio. So that's 0.65 equals e to the minus KT. What I did was I converted this log into exponential.
It didn't want you to do that.
But,
It didn't want you to do that.
well,
It works though.
let me see if I got the right answer. Okay, there we go. Okay. And then
7.8, I don't think the negative 3 here, right?
okay. So I did it another way.
You just,
I did it one way this way, and I did another way, and got the same answer. That's good. It's good that that happened. Because if you can convert it by going 2 different routes, then you're probably right.
you're probably most likely. I like how that one just didn't even try to put 3 in it. Just said 6.
Okay.
I guess the 3 don't matter if you round it, it's just 7.
Yeah. And now that we know K, well, actually, yeah, now that we know K, we could calculate the half-life.
We can do the bottom one. Bottom one.
Right. Well, that wasn't the question. But if we put 0.693 divided by this number, that would be the half-life. Okay, now for second order. So for second order, of course, we have a power of 2 squared A.
Because it's the second order is my problem.
Exactly right.
So the third order be like,
A to the third power. Yeah.
oh, well, that's not very hard, is it?
But we're not going there with all of this.
I know, but I'm just saying, it just means that the order is just consistent. I could just go that.
Yeah. Well, and like I said before, actual calculated orders aren't necessarily whole numbers. But we're sticking with whole numbers because it's easier to bring those characteristics into mind. That's a good place to start.
So far, I like it a lot better. This is easy to me.
Now, if you plot the data for a second order equation, raw data, you're going to get another curve. If you plot the natural log of second order, you're going to get a curve. But if you plot the reciprocal,
If you didn't get a curve, would it have been a first order?
yeah, if it's a straight line here, yeah, that's 0 order.
Yeah, and if it was a curve there, but a straight line there, it'd be the first order.
Yeah,
As long as it's a curve, that means you're doing good.
yeah, you need to keep looking if it's a curve. If you do it this way, if you take the reciprocal of A and plot it, you get a line with the slope of K,
That's a big one.
right? Like this, see? Positive K. When you plot 1 over A. And then 1 over A down here is the intercept. 1 over A, 0. Okay, so there's an example. We went ahead and plotted it natural log, and it's still a curve. So we plot the reciprocal, there you go, straight line. And this, I think, the reason the authors are settled with 0 first and second order is because the vast majority of equations fall under one of these 3. And sometimes you can do an approximation. For, say you have order comes out to maybe 1.96, say, that's close enough to 2. It should look like this. Okay, for a second order, the half-life is 1 over K times A0. Say before it was it's A0 divided by 2K, wasn't it? And then that was 0 order, first order, didn't have A in it. So that's the half-life for second order. Okay. Let's see, A0, if we start off with 5 molar, and the first 2 half-lives are 25 and 50 minutes. So if we start off concentration of A, we start off with 5.0 molar at time 0, right? Time 0. Then the first 2 half-lives are 25 and 50 minutes. So after 25 minutes, this should be half, 2.5 molar. And then after 50 more minutes, so we have 50 more minutes would make it 75, right? Total. Now we have half of this concentration. There we go. So now we've got a data set we can work with. write the rate law, so it doesn't tell us which one it is. Write the rate law, calculate K, and then calculate A at T equals 525. So when we finally get this information, then we put it in the integrated rate law because it has a time term in it. Okay. I think I've got this one in a subsequent slide. So rather than mess up the board. Okay, process of elimination. Notice that the rate law cannot be first order because half-lives are dependent on concentration. We noticed that the half-lives were different for each of them, right? And for the first order, the half-lives are not dependent on concentration at all. It's 0.63693 divided by K. So we know it's not first order. That simplifies things a lot. Now we just have to decide between 0 and second order. If the rate law were 0 order, then the half-life will be the initial divided by 2K. So why don't we do that? So here's the first one. The first half-life is 25. So 5 divided by 2K, solve for K is equal to 0.1. Okay. This is the first half-life, 25 minutes. This is the initial concentration. And that gives us 0.1 as our half-life. If we do it for 50, the second half-life, then our starting point is 2.5. Right? From this position where it was 5, replace 5 with 2.5 and the new half-life.
To get that answer, I mean, like K equals 5 over 50. To 50, you just replace the 25 with K to make 25 times 2 to make it 50. It's the same thing with the 50.
Well, we have to solve for K. It's unknown.
That's what I'm saying, though. You just switch to solve for K.
Yes. And now the K is 0.025. Right? That can't be. K is a constant. So we know that it's not 0 order. If it were 0 order, then these K's would be equal. So then by process of elimination, it has to be second order. But if we do the calculations, we can prove it to ourselves. Right? So we do the 1 over K times A0 and do it for each one, and we find that they're both the same. So that's the logic for saying it. We know it's second order, and we know this is the K. So if we write the rate law, let's see, K would go in here, and then we know it's second order. And then we need the integrated second order rate law, which would be the reciprocal. Right? Stuff K in here, and then just pick. Right? 525, and the initial after 525 minutes from the initial time, and this is the initial concentration, solve for that unknown, and it's got 0.23 molar after 525 minutes. Okay. All right. Okay, so there it is on one slide. Let's see. We're supposed to have a video.
I think that's supposed to do the concept check.
Okay. I wonder if that's one of those videos that's not supported anymore.
I don't know, it must be, because you didn't even have it.
Okay, that's good. That means I need to delete it. How can you tell the difference among first and second order rate laws from their graphs? But this is just reinforcement. Oops. It didn't give you the answer. Okay, so the answer is just plot each one of them. You've got time here, and then you've got the raw data here, and then you've got the log transform data here, and then you've got the reciprocal transform data here. Okay. So you got each of these data sets, plot these two, plot these two, plot these two. Which one's straight? The one that's got straight is 0 first or second order. That's where Excel comes in handy. Because you can put in the time in the concentration data set, and Excel will calculate those, and then you can take these and draw a chart, take these, draw a chart, take these, draw a chart, you just look at them. If you're comfortable with Excel.
I learned it last year. I need to use it for statistics too.
Yeah, keep using it.
I forgot how to use it, so I kind of have to try to learn that myself.
There you go. Okay. So what do we do if the rate equation has two reactants? It looks like something like this. The practical approach to this is you take one of them and you increase the concentration so high that it essentially is constant. It doesn't change. And that way you can modify this one to be rate equals K prime. It's not the same K because now this is relatively constant. This is combined with that to give you the new K. And then you run the experiment to find out what this one is. And then you go back and you hold this one constant. Now that you know what this one is, then you let that one vary. So the way we're going to do that is, this is our blue color that we see disappear in our spectrometer as the bleach works on it. And then we go back and do it again at half the concentration of bleach. And that's how we get it back.
That's going to be pretty cool.
Oh, it's fun. Okay. So this is what's known as a pseudo rate constant. Because it's not really the rate constant for that reaction. Oh, and I got the discussion is in the lab. Yeah. And there's some supplementary documents that I didn't print out. I don't think it's in this one. Let me look. It has been modified. So, okay, there's basic discussion. No. Oh, did you get this one? Yeah. That goes along with it too. I forgot to separate. And this one.
What is this?
This is like a sample.
Oh,
It's
lab we're gonna do?
a previous semester where we gathered data. We did one concentration time at one bleach concentration, and then the second one at different bleach concentration.
Yeah, this is the half, and that's the full.
These are the raw data sets, yeah. And then these are I took this data set, and did the transformations, right? This is raw data, this is natural log, and this is reciprocal. This one turned out to be the best.
Isn't that like the first?
That's first order. Yeah. So you should get first order for this reaction on the die. And then I have to show you how to, and we need to know the actual concentration of the bleach. So this is how we got the concentration of the bleach that's actually in solution during that reaction here, and then after that value of this. That's what these two.
Is this exactly what we're gonna do?
Yeah.
Oh.
This is how you treat the data.
Okay. I need to put that in other steps.
I would. Okay. So this is a summation of what we discussed, zero, first, and second order, and what the rate laws look like, what the half-lives look like. Notice that every half-life, zero, first, and second order, is proportional to the inverse of K. Notice that K is in the denominator for each one of these. Okay. The only thing that changes are these other factors. This one doesn't have concentration. This one has it with a 2 factor. This one has it with K on the bottom, K still on the bottom, with a 0 on the bottom instead of on the top.
I think it's kind of like the first one. I mean, 0 was flipped.
Yeah, well, you got,
Because the A's on the bottom, they're second, but on top for zero, and instead of 2K, it's K, but the one's on top, so it's like you're.
yeah. Now, the one constant, the one that doesn't change through each one of these is K's on the bottom, every one of them.
The first order seems like the easiest to figure out, though, just because you already given.
Yeah. Okay. So this gives you a feel, this exercise gives you a feel for what does zero, first, and second order mean to a reaction. If you start off with 5 molar A and the K value is this, and the only thing you change in that rate law is the order, 0, first, and second, what does that mean to the outcome after 30 seconds? If we do the calculation here, we find that after 30 seconds of a 0 order, you have 4.7 molar left over. So not much change has occurred. But with a first order, if you do that same calculation with a first order, then you're down to 3.7 molar. So the order says that the rate is going faster. And then the second order goes even faster still. You end up with only 2 molar after the same amount of time. And that's reassuring, because otherwise, what's the point? Well, what information does it tell you that you don't already know? Well, it tells you that this one is slow, this one is medium, this one's fast, relative to one another. Okay, now mechanisms. All right, I mentioned most reactions occur in steps, and that's where we get into mechanism. What step goes from here to here, and then here to here, and then eventually to products. These are called elementary steps of a mechanism. So an intermediate would be formed with, say, the first step of a reaction and used up in the second step. So the moral of that story is you don't see that intermediate. Right? It happens, well, you usually don't see it. There are methods now, usually involving laser pulses, where you can parse out the intermediates that might be formed in the process of a mechanism. But typically speaking, and for poor graduate students, you generally don't get to do that. You have to sort of guess, and that's what I'll talk about in a minute. Here's an example. If we're going to react nitrogen dioxide and carbon monoxide and make nitrogen monoxide and carbon dioxide, then this has been determined by methods that I'll describe in a minute to be the 2-step mechanism for this reaction. First of all, you take 2 of these nitrogen dioxides, right? That's nitrogen and these are 2 oxygens. You get 2 of these together and you get nitrogen trioxide plus nitrogen monoxide, okay? So here we've got this one right here that produces this. But this intermediate goes into the second step and it reacts with the carbon monoxide to produce carbon dioxide, nitrogen dioxide. Actually, nitrogen dioxide and carbon dioxide there. So notice that we use 2 here, but we get 1 of them back here. So overall, we've only used 1. That's why I put an X through them. Because they're intermediates that the intermediate doesn't show up in the product. Only 1 of them does in this case. So these are intermediate steps. But typically what happens is when you have 2 or more steps in a reaction like this, one of them occurs faster than the other. One of them is slow, one of them is fast, relative. So the overall rate of the reaction is dependent upon the slow guy, the weak link. So you can't go any faster than the slow one. That determines the rate here. I don't know which one is in this example. But we'll talk about it again in a minute. So when you're looking for a mechanism that gives you the rate of the reaction, you look for the slow step. That's the rate limiting step. Okay. Now, a few words about elementary steps. There are basically three types that are considered. Molecularity is what we call it. The molecularity of the step is unimolecular if the step is only one reactant. And one reactant means it's first order. So in the elementary steps, we can say something about the order based on the balanced equation of the elementary step. If it's bimolecular, you have two reactants, or you have two of the same molecule. It can go either way. You can have an A and a B, or an A and an A. That's bimolecular. But for this one, you have to have a collision of those two species. Either two A's come together or an A and a B. And that's a second order. And that's based upon, let's see, unimolecular would be this, producing product. And these are elementary steps. Okay, that's unimolecular. And then A plus A yields products, or A plus B yields some products. This is bimolecular. 1, 2. The coefficient here is 1 and 1, 1 and 1. So that's second order for this mechanism, for this elementary step, either one of these. Termolecular, you have 3. So you would say you could have A plus A plus A yields, or A plus A plus B, or A plus B plus B, something like that. Any one of these would be termolecular. Now, the reason we're making a point of molecularity is, what's the probability of these components coming together with the right energy and the right orientation to react in that elementary step? Well, this is a no-brainer. It's fairly common because it only takes one. Bimolecular is not much worse. You just need 2 coming together with the right energy and orientation. But 3, to get 3 to come together with the right energy and the right orientation of all 3 of them to make the reaction, it's very rare for that to happen. So when we're, huh?
How about 0 where we just not have one?
Yeah, I don't see a place for 0 order, because you got to have at least one of these to have unimolecular. But the overall would involve maybe more than one of these, right? Because these are steps, right? So when you combine the steps, that's where you get the overall 0 order. I lost my train of thought.
You're talking about how rare.
Oh, yeah, very rare. So when you're proposing elementary steps for a mechanism, you avoid this one unless there's no other way to do it. And typically what you do is use experience, intuition, other reaction mechanisms that have been determined, and propose different mechanisms with elementary steps. So this one might have 2 elementary steps, that's proposed. This one might have 3 elementary steps, not these, but you propose these mechanisms. And you might have half a dozen or 12 or however many possible proposed steps. And then you go in and start saying, that one's impossible, that one's impossible. You just eliminate them until you get down to the only one that makes sense. Okay, process of elimination. That's why you get graduate students to do the dirty work. So you're out on me too. All right. So this is what I was talking about before. The slowest step in a mechanism, the slowest elementary step, is the rate determining step. So the good thing about that is, if you know that the rate law for the overall reaction is limited by one of your slow steps, then you can use that information to derive the rate law from your elementary steps and say, does it satisfy the conditions, right? If you propose a mechanism and then you use what you think is the slowest step to derive the rate law and it doesn't agree with the empirical, then you know it's wrong, right? So that's part of the process of elimination. You take your theoretical and compare it to the empirical and see if it jives. If it doesn't, throw it out. First of all, when you propose a series of elementary steps for a mechanism, you have to be able to add them all up to the overall balanced equation. That's the first condition. If you cannot add them up, like we did with Hess's law, for thermochemistry, where you add them up to the proposed equation, if you can't do that, then you can't use that mechanism. It's not valid. And then, like I said just a second ago, the proposed mechanism has to agree with the experimentally determined rate law. And there's another one. It's chopped out. Okay, so here's an example. Decomposition of dinitrogen pentoxide to nitrogen dioxide and oxygen. So this is the proposed mechanism with 3 steps. So the first one takes one of these dinitrogen pentoxides right here, and it decomposes it to nitrogen dioxide and nitrogen trioxide. Okay. Then it takes this nitrogen dioxide, which is produced in this reaction, and reacts it again with that same nitrogen trioxide and makes nitrogen monoxide, oxygen, and nitrogen dioxide. So at this point, we've only used up one of these, and we've got one NO, one oxygen, and actually, no, one NO2. And now we have this intermediate that can't be there. It's got to be used up. So we take this one and this one, these 2 intermediates, react those, and they make 2 NO2s. So this NO2 and that NO2, this one's used up. All right, so this one's out, this one's out. This one's a bona fide product, that's a bona fide product. But notice we've got 1 here and 2 there. That doesn't add up to 3. Right. So what we would have to do is, we would say, we need 2 of these anyway, right? There's nowhere else in here. So we multiply the whole thing by 2. And that gives us 2 NO2s here. And let's see, maybe I've already done the work. Yeah, there we go. There. We got 2 of those, so that takes care of these 2. And then 2 of these cancel this one, right? These are on the left-hand side, these are on the right side. Now there are 2 of them. So 2 of these and 2 of those cancel. And then this one on that side cancels that one on that side. And then this one cancels that one. All right, so if we add these together, we've got two of these, that's good. And we've got one of these. Oops. How about NO2? 2, 3, 4. We're good. Yep. So we met the first condition. Add them all together, and you get the overall reaction. So that's satisfied. That part is satisfied. And the slow step in all of this is this reaction.
Got the longest one.
Huh?
I said the longest one.
Yeah, the messiest one, right, with these intermediates. So what would the rate law be for this one? Oh, we're not going to go there. We will. We'll do that with a different one. But for this one, okay, this is going to introduce the derivation of an overall rate law from the mechanism. Okay. If we have this reaction, A plus 2B, you'll see, and these are the intermediate, the elementary steps, A plus B equals D and D plus B equals C. First of all, can you add those together and get this? There's our C. Okay, C. D's cancel. One on either side. 2 B's and an A. Okay, so we met that condition. Now, if we're going to write the rate law, it has to be based upon the slow step. Right. Meets the first condition, yes. Summation meets the first condition. Okay. The second, this is the fast equilibrium. So if we write a rate constant for the forward reaction, we put it up over the top, right, on this arrow. So the rate constant for this reaction will be K1. The rate constant for the reverse reaction will be K minus 1. And we say that because it's a fast equilibrium. In other words, as quick as it goes this way, it goes that way. And then the rate constant for this one, which is slow, is K2. Okay. Now we have rate constants for each of the reactions, forward, reverse, and slow forward. So if this one's the rate determining step, then this would be the rate expression for the reaction. The K2 would be the rate constant, and times the concentration of D, which has a coefficient of 1, concentration of B, which has a coefficient of 1. So this is 1, and this is 1. Okay. But that D is not up here. We've got to get rid of the D. Okay. So we got to get rid of that D somehow. All right, let's go back to our initial setup here. Since the fast step is at equilibrium, the forward and the reverse rates are equal, then we can say that the rate expression for this one, forward, right here, that K1, A, and B to the first is equal to, is the same rate as the reverse reaction. Okay. Now we can solve for D. Solving for D gives us this expression, and then we substitute this into that equation for D. Let's see, substituting for D. Here we go. So this is D, right, from our previous expression, and then we condense it all, right? K2 times K1 divided by K minus 1 is our new K. And then A times B squared, right? B times B squared. So this is our rate law as determined by the mechanism. Then what we have to do is actually run experiments and find out what the empirical rate law is. Does it agree with that? Right? Is this one first order and that one second order? All right. So how are we doing? Got a half hour? How many more slides do I have? 24. Okay, let's kick it up a notch here. The collision model.
Count this one.
Okay. The collision model is one way of why things happen the way they do. First of all, molecules have to collide to react. That's a given. If they don't collide, no reaction. And when they do collide, they have to have sufficient energy for the reaction. That's our activation energy. How much energy does it take to break bonds and reform them? You got to have a minimum amount of energy to get that to happen. And this is dependent upon temperature. Temperature's higher, you get more energy in the reaction. And then they have to be oriented correctly. If the reaction sites are on this side and that side and they come together like that, doesn't matter how much energy they have, they're not going to react. So that's the collision model. They have to collide, they have to have enough energy, and they have to be oriented properly. That's why the term molecular is so rare, because it's almost impossible to get three molecules to come together with a proper orientation, no matter how much energy they have. Okay, activation energy. If we draw it as a graph, and we put energy on this scale, and the progress of the reaction on the x-axis, then these are our reactants, these are products. This says that from this energy state for our reactants, we have to add energy to get to here. And if we have just a little bit more, then we can get products. So this is our activation energy between, what is this one? What is it at this level? And when we get to this state, we're in a transition state or an activated state. Notice that if this is the energy of the reactants, this is the energy of products, then the products have less energy than the reactants. Where did that energy go? It's exothermic. Yeah, you give it up. So we could draw another one where we come over this hill and we end up over here. And if we did that, if we ended up over here, it would be endothermic, because you would put energy in, but you won't get all of it back. Okay. This is stating the obvious. Collisions have to have enough energy. And the orientation matters. And if we look at this intermediate, if these come together properly, then we start to break these two bonds here and start to form this bond here. So over here now, those bonds have been broken and this new one's formed. Oops, go backwards. There we go. Okay, this guy, Svante Arrhenius. I think he was Swedish. I believe he was Swedish.
They have someone else nicknames.
Yeah. He came up with this equation to describe the, to relate activation energy to the K value, the rate constant for a reaction. Now, this isn't very useful, right? Because we don't know what this constant is. We know what this constant is. That's the universal, the ideal gas constant. And this temperature, of course, has to be in Kelvin. And then this value, and this E is the base for natural logs. So this is the one that we don't know. Frequency factor, product of Z, whatever that is, collision frequency, and P, steric effect. So I suppose you could determine those, but there are other versions of this equation, fortunately, that are more useful. And this one, the linear form for the equation, plots the natural log of the rate constant against the inverse of the temperature. And then the slope of that line is the activation energy divided by R, and it's going to be a negative slope. Right, so it goes this way. And then this one is the intercept, the y-intercept. So what you have to do is determine the rate constant at different temperatures, and it will be different. Whenever you change the temperature, you get a different rate constant. So if we do that, if we plot those two, for instance here, right, if you have log K here and the inverse of temperature here, then the slope of the line is this value that we determined here. And that's the negative slope, or the negative E. So we can say this is equal to negative E sub A divided by R. And if this is equal to that, then we put in what that value is, and we can find out what the activation energy for that reaction is. Okay. Let's see. This, I don't know if you've heard this before, but a rule of thumb with chemists is if you increase the temperature by 10 degrees, right, 10 degrees Celsius, same thing because they're the same size units, then you double the rate of the reaction. So the question for this one is, what would the activation energy have to be for this rule of thumb to be true between 25 and 35 degrees? What would the activation energy have to be? Right? So that's a lot of information in one place. First of all, the temperature at 25 is 298 K, and the temperature at 35 is 308 K. That's the first thing. And then we're going to use Arrhenius differential equation. No, not the integrated equation. If we say this is the expression for that one, this is the expression for that one, and this is the K value for the higher temperature, which is equal to 2 times this K value. Okay? Because we said if we increase the temperature 10 degrees, it should double the rate. Okay, so if we ratio these two, and then we substitute here, now we have this value for one and this value for the other. Right? Now we have an expression we can work with. Well, as it turns out, this A cancels. And e to this power divided by e to this power is simply e to this one minus that one. So this one minus that one puts a plus sign here. So now we've got 2, because this cancels also. 2 equals e to these over here. And we can factor out 1 over t here and 1 over minus t here. And that makes the whole expression. That takes the e sub a minus outside. So we took the minus away from this one, we took a minus away from that one, made this one minus again. Okay, so what's next? Well, how do you deal with that? Right, e to that power. Well, the best way is to convert it to logarithm. That's what we're going to do next. So if we say, take the log of both sides. Right, so the log of 2 and the natural log of this one. So the natural log of e to a power, right, base e, is just a power. So by doing that, now we have this expression is equal to the natural log of 2. And in the process, I took that r from here and put it over there, right? Denominator and numerator. So now we can solve for e sub a. We have to substitute in what are these values for T2 and T1 and R, and we calculate that the reaction activation energy has to be 52.9 kilojoules in order for that rule of thumb to work. between those two temperatures. Okay. All right. So what's a catalyst? Well, we sort of know what a catalyst is. It speeds up a reaction. And as far as catalytic converters in the exhaust train of your car's engine, it speeds up a conversion of incomplete combustion products from your engine. It speeds up their conversion into more innocuous. It takes the oxides of nitrogen and the oxides of carbon and converts them into nitrogen gas and carbon dioxide. It completes the reaction. How does it do that? Well, basically what it does is, if you've got energy here in progress of the reaction, if you go like this, what it does is it lowers the activation energy, decreases the activation energy, which means more of the molecules have sufficient energy to make the reaction, which speeds it up. But catalysts, while they participate in the reaction, they're not consumed in the reaction.
What I've always thought of the catalyst is just like a little filter.
Yeah, right. It comes in one end and spits out the other end, apparently unchanged. But it did participate in the reaction. And the reason and the way it does that is it provides an alternate mechanism with different elementary steps to get from here to here. So it changes what happens around that reaction arrow. A different pathway is provided. This is another way of looking at it. So for an uncatalyzed reaction, this is the energy spread of all the molecules in your, right? You have lots of high energy, you have energy here, you have low energy there, and you have some that are really high energy, and these are the ones that have enough energy to react. Well, if you decrease the activation energy, what? You make more of them able to react. That's what we've done here. We just move the goalpost. Okay, different types of catalysts. Oh, sure. We'll pause. Okay.
That towel dispenser in the room is a little bit busted.
What's busted? Oh, the towel dispenser, yeah.
Wash my hands, I went to go get towels, and I said,
No, that's right. Okay, types of catalysts. They can either be heterogeneous or homogeneous. And what we mean by heterogeneous is the reactants and the catalysts are in different phases. So catalytic converter in your car is a perfect example. The catalyst is solid. It's platinum and palladium coated on ceramic matrix. They used to be beads, now they're probably some cone type shape.
that's the same example you used the last time we talked about catalyst.
Yeah, right. So they're in separate phases. And they depend, in this case, they depend on adsorption, which is a surface phenomenon. The reactants stick to the surface of the solid, and that makes them oriented properly with the right energy. Well, they've already got the right energy, but it makes them oriented correctly for that to produce the intermediate step.
By the way, it's a lot cooler out through there than it is in here for some reason. I don't know why. I went to the bathroom and it's like my hands are open to water.
Yeah. So when a heterogeneous reactant catalyst is used, you get this adsorption and activation of the reactants on the surface of the catalyst. And then they will even migrate across the catalyst to meet one another. And the reaction takes place, and then they desorb. That happens also in the hydrogenation of unsaturated fats to produce higher melting point products for restaurants and the like. We won't dwell on this. This is catalytic converter. I think catalytic converters used to have ceramic beads in here, and all you had to do is just punch a hole and they drain out, and then you'd plug the hole with something, and then you wouldn't have all that back pressure robbing your engine of energy. And increase your horsepower quite a bit. So my guess is they probably, now they don't use beads anymore. They use a matrix that can't be removed. Homogeneous catalyst. Obviously, the catalyst and the reactants are in the same phase. And this is characteristic of living cells. There's an aqueous matrix. The enzymes are catalysts. The reactants are dissolved in the matrix of the cell also. Or decomposition of hydrogen peroxide to make water and oxygen. That's not balanced. But if you add little potassium iodide, right, and the iodine is what does the work, that's the catalyst, then they're in the same phase, and you generate large amounts of oxygen very quickly. Okay. Another example, nitrogen monoxide and ozone makes oxygen and nitrogen dioxide, and then this is a free radical. This is a free radical. Reacts with this one to produce oxygen. And if you add these two mechanisms together, these two elementary steps together, you get ozone reacting with free radical oxygen to make two oxygens. This is how the ozone layer in the polar regions are depleted. But this doesn't have, let's see. Yeah, it does. Okay, so how do you tell which one is the catalyst? This one goes in as a reactant here, comes out as a product. That's the catalyst right there. If it were an intermediate, it would be produced over here and consumed over here. This is an intermediate. This is the catalyst. And freons do the same thing. Freons act like a catalyst. This one reacted with let's see, difluoromethane. Oh, there it is, freon 1,2. Ultraviolet light in the upper atmosphere, in the stratosphere, causes this decomposition and produces a free radical chlorine. So what does that mean? Well, free radicals are anything, molecules or atoms that have unpaired electrons. So chlorine, if we draw the Lewis dot structure, it would be like that. The chlorine atom would look like that. There's your free radical part. And they're extremely reactive. That's why, and usually you find chlorine like this. Right, that makes a bond between the two chlorines using one from one and one from the other. And they're less reactive. But this absorption of light splits off that chlorine. And that makes this a free radical too. And then that chlorine goes out and finds an ozone, forms an intermediate, and that intermediate is consumed in the next reaction, and then the chlorine free radical is regenerated, and it just goes off and tears up another ozone. So that's why these particular freons are bad. So the substituted freons that we use now are not as susceptible to that reaction. Oh, that's it. That's it. Okie doke. So we'll have that. We've only got 10 minutes left, so there's no time to discuss the lab. So just I hope you get your notebook by then.
I was supposed to get it today, so whenever I get home, I hope it's set.
Okay. And then
What size is it supposed to be? Because I got two different sizes.
it's supposed to be about that wide, about that
Well,
tall.
I know, but I mean like the 4-point something other or the 5-point something like the gram size. And
Oh, the size of little squares? I don't think it matters.
oh.
Yeah.
Well, I got the right one because I got two, so I guess I got.
I thought you meant the size of the book, not the size of the squares.
I was trying to make, because I had like little graph books at the house, but it was like a bigger notebook than the kind that we have here.
Uh-huh.
So I bought the kind that it looked exactly like you had, but it had like different size squares in it, so I didn't know if it mattered.
No, it doesn't matter.